Hi kids, this is Mr. Martin here. We're going to go over Chapter 17, Day 3 notes. The question at the top, it says, here's the example. I'm just going to read it first and explain everything that's going on. It says here, how much energy is required to raise the temperature of 45 grams of ice? Remember, ice is solid water. It is a crystal. It's at negative 10 degrees Celsius to gas at 155 degrees Celsius. So I'm going to explain how this all works out. So if we look at the sheet here, this graph breaks it down for us. So in this region here, from this dot here to this dot here, that is all ice. There's all ice in this region. I'll use my cursor. From this region here, this is all ice. It doesn't change. When it gets here to 0, it starts to melt. At B, we have both phases. We have a solid phase, which is ice, and we also have a liquid phase, which is the water. When it gets to the end of B, this is where it's all transitioned now to water. It's all liquid. There's no more ice. So then when it starts to heat up, it's still liquid, 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 and when it hits this location, it starts to boil. When it starts to boil, it's transitioning to vapor or gas. So at this plateau here, we have both a liquid and a vapor, a gas. When you get to the end here, this spot here, this marks the end of it and is all changed to a vapor, and we're continuing to heat up the vapor and putting energy into it all the way to the top, 155 degrees. So in this first gap here, it's ice, right? And then in this next gap here on the rise here, this is liquid. I guess I could put here solid for ice because it is solid. And then over here on the other end, this is vapor or a gas, right? So we have those three phases happening, solid, liquid, and gas. In the plateaus, and I'll circle those, at B, we have both ice and water. We have solid and liquid. Up here at D, we have liquid and gas, a vapor. We have both of those. So what we're trying to do, according to the question, it wants to know how much energy. And remember, energy is given in joules. So if you look at our constants, and the constants are really important for this problem here. So the delta H, or the heat of fusion, is equal to 334 joules per gram. Joules per gram. So that's telling us how much energy per mass. How much energy per mass. So if we need that, that's going to be at a plateau because there's no transition, there's no change in temperature. Notice that it's just joules per gram. So it's going to tell us how much energy in a mass. So this is for a plateau B. I'll put here B. All right, for this guy here, delta H for vaporization, that right there is for the other plateau, D. So I'll put that here. We need that at part D. Why? Because when things are vaporized, they go from a liquid to a gas. This next one down is a little different. Specific heat capacity, that's how much energy is put into an object or some sort of material, and the material acts like a sponge. So if it takes a lot of this energy, then it's going to absorb the energy and it's going to hold it for a long time. If it's very little, it doesn't absorb very much, and it gives off very quickly. So notice liquid water here is 4.18. That means it takes a lot of energy to heat it up, but once it's heated, it holds on to it. Where ice, not so much. And then you can see that gas is pretty close to ice. So they have pretty similar specific heat capacities. But it says here joules per gram degrees Celsius. So it does depend on the mass, but it is a change in temperature that's really big here. And so that's why we use these slopes here. This first slope here is ice, and so we're going to use the specific heat capacity for solid water, 2.06 joules per gram degrees Celsius. So we'll call this region A. Right? Then the next slope here is all liquid, and this is C. So it's C. And the last one here, the last slope of gas is E, and so we'll call this one E here. So that's how it's broken down. And you have to use them, and at the end of this, we should end up with the units of joules. That's what we want. We want this energy in joules, and then we're going to add them all together. So we're going to break it down by segment. Here's segment 1. Starts at negative 10 degrees and goes up to 0 degrees. So if you do this one, this is where part A is. Part A is segment A. It says here, find the energy required to raise the temperature of 45 grams of ice from negative 10 degrees to 0 degrees. This is part A, from right here to here. All right, I'm just going to show you the equation, because what you're going to do is you're going to start with the specific heat capacity for water. I'll use a little bit of paper here to kind of mark it out for you. So there it is. I'm going to show you. There it is, 2.06 joules per gram degree Celsius. So it's just like anything else, use the units. So if I want joules to be my final unit, I need to cancel out grams, I need to cancel out degrees Celsius. So from negative 10 to 0 is obviously 10 degrees Celsius. So I'm going to put here delta T is going to be 10 degrees Celsius. That's the change. So watch the setup now. So I start with the mass, which is 45 grams, and notice that the grams cancel out. And then I'm going to do the next, which is the 10 degrees C. The 10 degrees C comes from this change from negative 10 to 0. It is delta T, the change in temperature. So if you go across and you multiply this whole thing out, you're going to get this answer of 927 joules. This is just for part A. This is just from this segment here to there. It takes 927 joules. All right, that's not our final answer. That's just the answer to one segment. So I wrote out this little set right here. It says heat, which is in joules, is specific heat capacity times mass times delta T. CPm delta T. There it is. All right, so now let's go on to the next. And once I think you see the next one, you'll kind of get the rest of it. It is part B. Sorry about that. So part B is the plateau. It's this little plateau here. And so if we go all the way back up to the top, where we use the heat of fusion, 334 joules per gram for part B. It's this plateau. Fusion, because it's going from a liquid to a solid. It's fusing together. It's fusing together. All right, so now let's see what it looks like. So it says find the energy necessary to melt 45 grams of ice as it's at its melting point, which is 0 degrees Celsius. So then we start with this heat of fusion, 334 joules per gram. And guess what? I need to cancel units. I need to get rid of this grams, because then I'll be left with joules again. So all I do is I use the mass of the ice. And look what happens to the units. They cancel out. So if you multiply these together, I get 15,030 joules, but I need to use significant digits, and so I end up with 15,000 joules. This 0 here stays the same. Stays the same. So there's 3 significant digits here, 3 significant digits here, and then there's more than 3 here, and I need to, so this one has 4, so I need to go back down to 3. So that's why we use this 0 with the bar over it. Just these 1, 2, 3 significant digits. So for B, this region here is 15,000 joules. All right, so now it's 15,000 joules. I have 927 joules, 15,000 joules. Next, I need to do part C. So it's going to be on the next page. I'll flip the page over. All right, oops. So what I'm going to do is I'm going to show you this page here. This is the original page, and we're going to refer back to this graph. So remember, we're doing part C now. So I'm going to bring that question up, and here it is. Here it is. So it says here, how much energy is required to raise the temperature of 45 grams of liquid water from 0 to 100? So from 0 to 100, and remember delta T Delta T is where I'm going to subtract. I'm going to subtract 100 minus 0. It ends up being 100 degrees Celsius, right? So that's the temperature change. So now that we know that, what do we start with? Well, now that I'm in the liquid phase, I need to choose the specific heat capacity for liquid, 4.18 joules per gram degree Celsius for part C. So I start with this here. 4.18 joules per gram degrees Celsius. All right, so just like we did last time, we have to find the mass. And we said the mass was 45 grams. Same as it was before. It doesn't change, but the grams cancel out. Then we go on. There it is. There's the delta T, 100 degrees Celsius. That cancels out. So then we end up with joules. Again, use significant digits. If there's 3 here, and oh, there's 4 here, so we have to use 3 significant digits. And so this would end up, when the 1 makes the 8 stay the same, 18,800. So this liquid phase here is 18,800 joules. We're almost there. We have to do part D next. And for that one, we need the heat of vaporization, 2,260 joules. And that's what it says here next. I'm going to show you right here. Scoot this up a little bit. Here it is. How much energy required to vaporize 45 grams of water at its boiling point? And that boiling point is right there, that flat plateau. So it takes 2,260 joules per gram. This right here is the heat of vaporization, 2,260 joules. It comes from, it's a standard for this vaporization, meaning that it's transitioning from a liquid to a gas. So all I need to do again is cancel out the grams with how many grams? 45 grams. The mass never changes. So those grams cancel out here, I'm left with joules. There it is, 101,700 joules. But since there's 3 significant digits here, 3 significant digits, I need to have 3. This 7 will bump it up to 102. There it is, 102,000 joules. So for this entire piece here is 102,000 joules. All right, now we're on our very last one where we have to calculate the energy for that last rise where the steam is rising. And so what we do for that is we are going to use, I'm going to scoot this down. For that last phase here, since it is on the rise and it's a change in temperature, it is obviously a specific heat capacity. Any change in temperature, you're going to use the specific heat capacities. This is plateaus, heats of fusion, heats of vaporization. So delta H's are for plateaus. CP's are for change in temperatures. All right, so for this last one here, I'm going to use this guy here. The specific heat capacity for vapor, the water vapor, is 2.02 joules per gram degree Celsius. And so it looks like this. I'm going to scoot it on down. Here it is, 2.02 joules per gram per degree Celsius. And then here it is, the change. So if I'm going from 100 to 155, delta T, I'm going to subtract those two, and it turns out 155 minus 100 is just 55 degrees Celsius, right? So I'm going to set it up now. So I use my specific heat capacity first, times my mass. The mass cancels out, and then I'm going to multiply by my change in temperature, and there it is. I'm left with joules again. I do the math, and look, here it is. So again, 3 significant digits, and I have 1, 2, 3, 4, 5. So I need to change this. And believe it or not, it rounds up to 5,000, but remember, use that bar to signify the significant digits. Just these 3 are significant. All right. So now, going back to our graph, I'm going to use the graph up here. I'm going to show you everything here. So this is 5,000 up top here, joules. So at the bottom, 927, 15,000, 8,800, 102,000, 5,000. We need to add all of these up. I need to add these, add these, add these, add them all up, and the total energy will be our total answer. So that's the last step. right here.